Hello, I'm David.
And I'm Dan.
And we're the founders of Aircraft Safety Solutions, NDP 5392, which is our processor. During this presentation, we will give our mission statement, some details and block diagrams about the NDP 5392 and how we came up with that awesome name. And we're just going to talk about a couple of enhancements and end with the Q&A session.
But first, a little bit about our company. We're committed to developing the best system that we can offer and providing our clients with the best possible service. Our goal is to create interesting systems to help and meet the demands of our clients and to keep aircraft safe and secure.
A little bit about the NDP 5392 and how we came up with that name. It stands for Named Digital Processor, serial number 5392. It's an experimental processor that utilizes a RISC architecture, or reduced instruction set architecture. The philosophy behind RISC is that is to create a rapid executing and simple architecture that where memory can interface to load and storage.
The NDP 5392 uses a Harvard memory architecture where instructions and data are separated into their own respective memory modules. Here are some details about it. The memory operands in the NDP 5392 are stored in Little Endian format. This is a format where the lower significant bits are at the lower addresses. As you can see from the example, the least significant bit is placed at the lesser significant data addresses.
Our processor supports various instruction formats. R-type, I-type, the typical ones. Jump instructions, and
Can you go back to those formats for a second?
oh, yes.
Yeah, back one page. So R-type is what we call triple format. I-type. Got it. Okay, thank you.
And now, without further ado, the NDP 5392.
This is our processor.
It has three memory modules. The data memory, instruction memory, and input and output. It also has a central processing unit as module as well.
Inside the CPU module is a control unit, and it produces the control words to engage the execution unit here. We have a lot of control words.
This is the execution unit. It contains the BIU, the floating point data path, and the integer data path. All of these, the execution unit performs the operations and calculations of the processor.
Inside the BIU are various registers, multiplexers to switch between data lines, and certain logic to control it.
This is the write and the floating point buffers, which they have similar functions. These registers contain the data that is to be written to data memory.
The RD buffers contain the data that is to be written to the floating point registers or the integer data path registers. Once filled with data, they are combined into a 63 or 64-bit bus.
The MAR, or the memory address register, accepts data from the integer data path and contains memory addresses for interfacing with the data memory module. The stack pointer contains the address of the stack and is pre-decremented on a push instruction and post-incremented on a pop.
the instruction pointer right here, and contains the addresses for the instructions, and IR sends data into to the SATA extended into the integer data path.
As a consequence of the utilization of if and else statements, we have many control lines for the control unit, but we think it helps to create a clear understanding of the control signals to the program. As mentioned before, inside the execution unit is the floating point data path and the integer data path. The floating point data path handles floating point numbers, and the integer data path it handles integers. As you can tell, that there wasn't any significant changes from the baseline. Each register file has 32 individual registers for ALU operations, and each register is 64 bits wide.
And now, a few enhancements that we have made. To exchange two registers quickly and easily, we created ALU operations, swap 1 and 2, which puts into a temporary register the data of one register, and then the next instruction would have the swap 2 ALU operation, which outputs the temporary register, so that you can easily and quickly swap the two registers. And we also included the ability to manipulate the flags independently for various reasons.
Where was the carry handler register?
Oh, the carry handler register is the temporary register in the ALU.
Is it clocked?
Yes.
No? Yes?
Yes.
The ALU wasn't clocked. Did you guys change that?
Oh, hey. No, we actually didn't add a clock to the ALU. It's just a temporary register.
So it didn't present any timing problems?
No, not really.
Not really. Okay.
And some future enhancements that we were considering is to optimize our BIU to use less control words, possibly by using case statements. Maybe adding a barrel shifter to the secondary source for modification of it between the ALU and register file, and backup cores for redundancy systems for aircraft, so that it'll be safe.
And that is our presentation. Is there any question and answers?
Or questions?
Questions?
I made that one.
So what has this got to do with airlines or air flight or aircraft systems at all? What instructions or what?
Well, we're mostly focused on our future goals of our company, and we wanted it to apply to aircraft and create redundancy systems for it, for just in case there's like a failure in one CPU, there are backup CPUs to.
But what did you do toward that end? It just looks like it executes the baseline, but no hardware enhancements to hook into doing redundancy. So it's just a thought, you mean?
Yeah, it was a thought, because we were actually thinking about having a comparator for the data, the ALU, the CPU going through it,
Mm-hmm.
and then if one of these aren't right, based on the other CPUs, then it'll alert a flag, but it'll also still be able to run by switching to the other CPUs. It's in case of hardware malfunction or drastic failure.
So that would be done by what means? You said comparator. What would you be comparing?
Just the data
At what level?
at the level between the memory and the execution unit.
Like, would it be a clock level comparison or after instructions done comparison, or where do you do the comparison for redundancy?
Every time after data is received into the
What do computers do? 'Cause I'm not sure what after data is received means. Just for everybody, because you may have some insight here that we're not, you should lead us into.
Well, the CPU, they send data out to the, or say you want to do different operations, like add or something.
So that's an instruction.
Yeah, instructions. Each one sends out the result of the add.
Well, they don't send it out, though. It just goes in the register file. That's what I'm trying to get at, what you were thinking about as far as...
Well, if you were to write to memory. If you were to write to memory.
But what if you didn't write to memory? How would you do redundancy? What if one of the ALUs, the main ALU failed, or, the register file results were not the same? So at what level are we checking? That's what we're trying to get at.
I suppose we should be checking it at the ALU, at each,
or at least the result of every instruction.
Yeah.
Kind of thing.
At the result of each instruction, and also between memory and.
So have you done any research into redundant systems and how they actually do redundancy?
I actually have not.
5392, what's that? What was the significance of 5392?
I thought it sounded cool.
Oh, okay. 53.
And it sounded efficient.
And then you use the word experimentation. This processor is an experimentation or something.
Oh, an experimental process?
Yeah, experimental processor. Well, what does that mean?
Well, it's just the first processor that we've done, and we were hoping to continue working on it and maybe adding the enhancements for the future.
It's a good word, though. I mean, I like that. But that's why I thought maybe there was some kind of hooks in there for, redundancy or something. Because definitely in aircraft systems, space shuttle, I think it had 6 computers that all talk to each other or something like that. It's an interesting concept. So I thought maybe you'd been involved. So anybody work for an aircraft company that does this?
Actually have not.
Just an interest.
Yeah, I'm just really interested in redundancy
Yeah.
systems for aircraft and aircraft safety.
Other questions? See, the second day is a little bit more detailed, so be ready. I want you to go back to your the logic you showed us for since this is hardware design reviews, right? Like the stack pointer, the MAR, you had some if-else statements and that kind of logic. So since we're doing hardware here, yeah, any one of those, like the MAR, that's good. Okay, what would happen if the load and the ink were asserted at the same time in your system? At the same time, in other words, somehow that was an error, obviously, but what would happen in your system if that happened?
In our system?
Yeah. So load is asserted on the same cycle that ink is asserted. What would happen?
Well, it'll accept the inputs and then increment it, but
No. Load is asserted. MAR out will get something. Ink is asserted. MAR out will get something. What will MAR out get in that particular case? Same thing would apply to the stack pointer or any of these.
Seems like it has to be nested, or it has to be.
We never use ifs like that as design engineers, and we're here just for design reviews and things. And so this is what we want to learn and pick up. That's why we always use a case statement, because a case statement will only allow one, or the default.
Okay.
So you never just do if else, if else, if else, if else, because you're going to have errors. Potential. It doesn't mean it was. So, and we always have to design for the worst case, not, everything's going to be as it should be. And so in all of those cases, you could have failures if there was some kind of glitch.
Since they're non-blocking, would it just be the last one, or is that not how it
That would be probably how it works in this case. But the thought should be there as a designer. That's why we're in school. That's why we do things. That's why we have reviews, so we learn from the design reviews, design techniques. And so we're doing combo logic. Just use the case statement. And then it guarantees you got a default case, even if all the control signals got scrambled.
I wasn't clear on, maybe I just missed it, where you put your flags register and how you handle that.
Our flags, we didn't cover it. The flags for the floating point or the flags for the inner data?
Both. I was just curious how you develop them.
In other words, you had to push it, you have to pop it. Where was that register? Was it in the control unit? Was it in the BIU? Was it in the...
It doesn't, the flags going to the control unit to be modified by or...
So in other words, who did the code for interrupt when you had to push the flags?
The interrupt code is in the...
Yeah, but somebody had to write it, the steps for return from interrupt and interrupt. Did Dan write it or did you write it?
I wrote it, but I can hear it too.
Okay, so you had a problem in there. Okay. No, any more questions?
No.
It was a good presentation, you guys. It was. It was good. Thank you.